Could I have a volunteer to open the class with prayer? I'll do it. Our dear kind Heavenly Father, we are gathered here today to learn about the laws of thy kingdom that govern the universe which thou hast created. We are mindful of our place in that universe, that as insignificant as we are, that we are loved and we are cherished. We're grateful, Father, for the opportunity to associate one with another and to have this chance to help each other. Father, we ask a blessing, a special blessing upon these young people as they are facing so many decisions and so many obstacles, so many challenges. Please help them. Please watch over them and guide them, give them courage and comfort. We ask now that our minds might be open, that we might be able to concentrate and piece together the ideas that are going to help us to understand this magnetic phenomena. And this we ask in the name of Jesus Christ. Amen. Amen. Okay. We're going to start with a simple question that you can see. You're just going to have to intuit. I guarantee, I promise you, there's a problem like this on the exam. Okay, I know it in my guts. Because I took the exam over to the testing center yesterday. So, what direction is the magnetic force on that electron? And these are your choices. I'm going to get you started on your clicker. Okay, now you can click. Okay, last call.
Going down. No, you're still gonna be on.
Well, some of us aren't ready. Okay, some of us aren't ready for that exam. So let's do this together. I like this problem and problems like it because it emphasizes the fact that these magnetic force problems are a two-step dance, just like the electric force problems were previously. Something sets up a magnetic field, and then that magnetic field pushes on something else. In this case, we're ultimately looking for the force on the electron, so it's the something else. And that means that the wire is what's setting up the magnetic field. And that magnetic field, I know from right-hand rule number 2, if I put my thumb in the direction of the straight current, my fingers wrap in the direction of the B field, the magnetic field, so it comes out on this side and in on that side. But I don't care what's going on over here. I care what's happening where the electron is. And over where the electron is, the magnetic field is into the page, into the screen. That's step 1. Okay. Now, step 2 is we use right-hand rule number 1, which is the only right-hand rule that gives us a force. You don't have to be wondering, which right-hand rule should I use for a magnetic force? There's only one, okay? And we reach in the direction of the motion. There has to be motion for there to be a force. And then we turn our wrist, this is the most important step, so that we can wave in the direction of the B field. that puts my thumb up. And that's the direction of the force on a positive charge, like a proton. If it's an electron, you gotta reverse that. And so the answer is down, okay? See if your neighbor got that right. If not, you know what to do. Yes. That's what I did. That works. Make it impressive. Okay. Now, this is another one that, you know, if you don't get this one right, you're not ready. Don't go to the testing center until you see how to solve these problems. We have this copper loop that is being moved to the left next to this wire that's carrying conventional current down to the bottom of the page. And so the question is, what direction does the induced current flow in the loop? Is it going to be clockwise, counterclockwise? C is not the right answer. So you can click. Okay, get your vote in, last call. Okay, that's better. That's who you invite to your party, okay? They're gonna have the most fun. The answer, of course, is clockwise. Now, these 24 people are not ready. And I suspect that some of these 102 people were flipping a coin. You know the truth about whether you just guessed right or whether you figured that out, okay? But if you didn't figure it out, you need to figure it out before you go to the testing center. So let's do this together. Again, the first thing we need to know is, how is the external flux changing through that loop? Well, what do I mean by external flux? Well, that's field lines. That's what flux means. Field lines due to anything that's not the copper loop. Well, that's going to be field lines due to the wire. Well, I know by right-hand rule number 2, if I put my thumb in the direction of the current, that the field lines are going to be going into the page over there. Okay. And I know that those field lines are going to spread out when I get further away from the wire. I've got a strong magnetic field close to the wire. I've got a weak magnetic field away from the wire. So if it helps to put numbers in it, do that, okay? I got 65 field lines going into the page here. When it gets here, I've only got 5. Fight the change. They're dying. I had 65, now I just got 5. They're dying. What am I going to do? I spend field lines in or out? In. I'm losing field lines in, so I put field lines in. Now use your right thumb to represent that induced flux, that magical, not sure where it came from, flux, and your fingers are going to tell you the direction that the induced current has to flow to make those field lines clockwise. Okay? See if your neighbor's on the bus. Do a buddy check. We work these problems with inductors in the same way we work the problems with capacitors. We essentially replace the inductor with what it's acting like. When we first try to change the current through the inductor from nothing to something, the inductor fights us and it won't let us instantly change the current. You can't go from 0 amps to 3 amps all at once. And so that means that right after I close that switch, there's nothing flowing through that inductor. It takes time to build up the current through the inductor. And so initially, right after I close the switch, it is acting like an open switch or an empty socket there. Now, if that's acting like an open switch, replace it with an open switch. And then just go back to what you know about circuits. You know that nothing's gonna go down this path because it's not a complete path. And so that means all the current that leaves the battery has to go around this loop here. And so if I am looking for the current, the magnitude and direction of the current through the battery, I would use Ohm's law globally. Since I'm going around this inner loop, the equivalent resistance around that loop is 120 ohms. And the voltage of the battery is 240 volts. And that's going to give me a current through the battery that's equal to 2 amps. And it's conventional current we always talk about. So it's going to go up, leaving the positive terminal and going around. Okay. Now, we're asked the voltage difference across the inductor. Well, if I want the voltage difference across the inductor, I treat that as an open switch. And you remember when we're looking for voltage across an open switch or an empty socket, we look away from the sun. We look to the other parallel branch to see what its voltage is across it. And I know that I have 2 amps flowing through R2. And so that means that the voltage across R2 is going to equal to 2 amps times 40 ohms or 80 volts. And I also know that on this parallel path, the voltage across the inductor plus the voltage across R3 have to be the same, 80 volts. And there's nothing flowing through R3, so there's no volts across it. And so that means that the voltage across the inductor has to be 80 volts. That makes sense? Okay, look away from the sun. Well, now the next time that we can talk about is after the switch has been closed a long time. After the switch has been closed a long time, the current through the inductor, if I close the switch here, that current ramps up to its final value. Okay. The fight, the EMF, which is given by Faraday's law across the inductor, is going to be minus L di dt. But if this gets up to 1.2 amps and 1.2 amps and 1.2 amps, my change in I is 0. And so that means that inductor stops fighting. And if it has 0 volts across it, it's acting just like a wire, just acting like a wire. And so I would replace that inductor with a wire and ask, what does it look like now? Well, if this is a wire, this whole thing this is part B. This whole circuit looks like 80 ohms. And then two branches each with 40 ohms. Okay, and that's 240 volts. So the current comes out of the battery. It splits right there. Half of it going down this path and half going down that path. And it's only 50-50 because the two paths look identical. They each have the same amount of resistance. And so the question is, what is the current through the battery now? Well, I have to replace this circuit with a single resistor. We call that the equivalent resistance. And I know that 240s look like a 20. And if 20 is in series with 80, that means this is going to be 100 ohms. And it's 240 volts. And so if I use Ohm's law, V equals IR, globally, this is going to be 100 ohms now. I'm solving for the current through the battery. This is 240 volts, and that gives me a current through the battery of 2.4 amps up. Now, the voltage difference across the inductor, it's acting like a wire. So it has 0 volts across it. How we doing? Okay, part C is always the same. You've got that physical switch closed for a long time, long enough for that current through the inductor to build up to 1.2 amps. Okay, after a long time, it's just a constant 1.2 amps. And then we throw that switch open again. Well, by throwing that switch open again, the current through R1 goes to 0 immediately. The current through the battery goes to 0 immediately. They're no longer on a complete path. But what we can't change immediately is the current through the inductor. Okay, that we have to ramp down. That takes time. So right after I open that switch, it's still 1.2 amps. It's still 1.2 amps. And so right after the switch is open again, it acts like a battery where it's driving 1.2 amps around this loop there. And so if I want to know the magnitude and direction of the current, if any, through R2, well, since the current was coming down through the inductor before I open the switch, it still has to be going down through the inductor after I open the switch. And that means it's going to be going up through R2. And I can find that current. I can find that current by just saying the current through R2 is equal to the current through the inductor, which is going to be 1.2 amps. And it's going down through the inductor. So up through, oh, you can't see that. Huh. Up through R2. Now, the voltage across the inductor the inductor is now acting like the battery. And so I just use Ohm's law. I'm gonna have 1.2 amps, and it's going around those two resistors, R3 and R2, are now in series. And so my total resistance in that loop is 80 ohms. And that's going to give me a total of 96 volts. Did I do that right? That's amazing. Even at my age, I can still get that done. Good sir in the back. I will wait till I get back there. I had my hearing aid service at Costco last night, but still marginal. Oh, do you see how I got the 2.4 amps? The 2.4 amps was going through the battery. And then it split 50-50 between the two paths, because each path had 40 ohms. Yeah. Okay, are these extras? Okay. Are there questions on this problem?
So in this question, theoretically, L could have been any value.
What's that?
L could have been any value in this question.
Oh, thank you for bringing that up. I'm always going to give you the value of L. And if you find that you are using the value of L, rethink your life choices, okay? Because that's not important. If I knew how quickly I was changing the current, I could use this formula. But I don't, okay? So the only time I ever use this formula is to justify why it's acting like a wire. Thank you for bringing that up. Okay, again, a promise that I'm making to you is that there will be a problem on the exam that just has an inductor in it without a capacitor, okay, like this problem here. That is similar to this problem that you had for homework. Okay, this is one of your homework problems. And you'll notice that this is maybe even a little bit simpler than the one we just worked. But again, we solve it exactly the same way. We essentially just first pretend the inductor is an open switch. Then in part B, we pretend it's a wire. And then in part C, we pretend that it's a battery, okay? And so this is the homework that is due this evening. Right after the switch is closed, we call this a open switch. And that means that none of the current is going to go to the right. It's all going to go to the left. And so I just have a very simple circuit here. V equals IR is going to give me 4 amps running through that loop. Does everyone see that? 200 volts, 50 ohms. V equals IR gives me 4 amps. Okay. Well, a long time after the switch is closed, this inductor is acting like a wire. And if this is a wire, the right side of this circuit looks exactly like the left side. And you'll notice that these two sides, the two branches, left and right, are parallel across the battery. They're independent of each other. What's happening over here isn't going to affect what's happening over there. And so that means now I still have 4 amps going through the left, but now I also have 4 amps going through the right. And so my current through the battery just changed from 4 amps up to 8 amps. And the current through the inductor is going to change from 0 when I close the switch up to 4 amps, 4 amps, 4 amps. Okay? Now, if I open the switch, I remove the battery from the circuit, and the only thing that can't change in this circuit is that current through the inductor. And after the switch has been closed a long time, the blue line, I had 4 amps going down through the inductor. That can't change instantly. That takes time to ramp it down. So this is going to turn into a battery that's going to drive current, the only path it's got left, because I've removed the center path, it's got to drive it all the way around the outside. So now the 2 resistors are in series. R1 and R2 are in series. And so I have a total of 100 ohms. The inductor has to keep 4 amps going through it. V equals IR means that this inductor has to act like a 400 volt battery. Okay, twice as big as the original battery. 400 volts. Check that your neighbor is going to get this problem right when you get to your homework, if you haven't done it already.
Because now we're in parallel. Everything's connected. So if it's a ball line,
Okay. As long as we're doing your homework for you. This is 17-3. And I have a feeling that you might have a problem like this on your midterm. Okay. Now, again, if you look at that problem on line, you'll see that it has 3 parts. The A, B, and C that we've been seeing over and over again. The part A are all the questions that are right after we close the switch. And right after we close the switch, now the capacitor is empty. And that's on me. Okay, my bad. Remember, capacitors act the opposite of inductors. The voltage across the capacitor depends on the charge stored in the capacitor divided by its capacitance. And with a capacitor, that's what can't change instantly. That's what we have to ramp up as a function of time. So if I close the switch here, I've got to ramp up that charge to its final value. Now, that means that this is going to act like a wire right after I close the switch, and the inductor is going to act like an open switch. So what you do in these problems is you just replace them, okay? Replace the capacitor with a wire and the inductor with an open switch. And then you go back to what you know about circuits. You know in this circuit that nothing's going to go through B. B is going to be dark. It's going to be out. It's going to have 0 volts across it, okay? And that means that all of the current is going to go through A, C, and D. And that means that they are now in series. So let's draw this over here. If all of the current that flows through A has to go this way, and I've got a 90-volt battery, these bulbs are all equally bright. And the voltage has to add up to 90. So this is going to be 30 volts, 30 volts, 30 volts. This is out, so it's 0 volts. And since I have 60 volts from here to here, this must be 60 volts across the inductor. Does that make sense? Okay, questions on part A? Well, now we look a long time after the switch is closed. A long time after the switch is closed, the capacitor is full. You've got it up to as much charge as you're going to put into it. And it's saying no more charge can come down this path. I'm full. So the capacitor is acting like an open switch. The inductor has stopped fighting. And so the current through the inductor is constant. So the inductor is acting like a wire. So I just replaced the inductor with a wire and the capacitor with an open switch. So let me draw that. So this would be for part A, right after the switch is closed. For part B, the long time after the switch is closed, I've got a so now all the current that goes through A has to go through B. They are going to be equally bright. And since this is still a 90-volt battery, this is going to be 45 volts, and this is going to be 45 volts. Okay. So, what's going to be the voltage across the capacitor? Well, if I've got 45 volts from here to here, that's going to be true regardless of which path I take from here to here. So that means along this path, I have to have a voltage difference of 45 volts. I got 0 volts here because it's dark, 0 volts there. So I've got 45 volts here. If I want to know what charge is stored on that capacitor, I'm just going to take Q is equal to the capacitance times the voltage. And that would be 1.5 farads times 45 volts. And I want you to recognize that full means different things in different circuits. It rarely, almost never, means the battery voltage, okay? In this problem, it's 45 volts. In other problems, you've had different values. You just have to look away from the sun and look at what voltage you have on the parallel branch. So this would be, is it 67.5 coulombs? Did I get that right? Let's say I did. Okay. Again, amazing. Now, part C is where people start to have trouble. And when I say part C, that's not part C in your your homework problem. It's the third time we could talk about. After the switch has been closed a long time, we throw it open. Now, if I throw that switch open, the battery's out of the circuit. Bulb A goes dark immediately, okay? But the two things that I can't change are the current through the inductor and the charge in the capacitor. Now, the charge in the capacitor, that makes that one easy, okay? It had 45 volts across it when the switch was closed. When I throw the switch open, it's still got 45 volts across it. So if I, so if I draw the circuit, it looks like this. And I know that this one was, the capacitor was charged up to 45 volts. So it's still gonna be 45 volts right after I open the switch. What I can't change instantly is the current through the inductor, okay? That has to be exactly what it was before. And now you can see that that current through the inductor is gonna have to go around counterclockwise like this. And so that means that B, C, and D are going to be in series. Are you with me? Now, yes,
How do you know if the inductor and the battery are working together or not?
how do I know that they're working together?
Is there an induced current being caused from the battery of the capacitor onto the wire, onto my inductor? How do I know my induced current's going the same way?
This has to be a 45-volt battery with the size, with the side closest to the positive terminal of the battery being the positive side. So it's gonna push this way regardless of the circuit. For the inductor, you look at what direction the current was traveling through the inductor in part B, that has to stay the same. So, if they're fighting each other, they're fighting each other, but the ultimate current has to go in the direction that it was going through the inductor before you open the switch. In this case, the inductor's gonna try to keep that current going, and so it's going to turn into a battery pushing counterclockwise, the same direction that the capacitor is pushing. So in this case, the inductor and the capacitor are helping each other. But the thing is, I don't know how many amps were going through that inductor before I open the switch. Do I? Right? I didn't know where I bought the bulbs. I didn't know how much resistance those bulbs had. However, I knew that the current that was going through this inductor in part B was enough current to give me 45 volts across bulb B. Bulb B was 45 volts bright. And that means that it's still going to be 45 volts bright. Because the current going through the inductor is the same as the current going through bulb B, and it can't change instantly. Well, C and D are in series with B. They got to have the same brightness, so they're also 45 volts bright, 45 volts bright. And so I've got 135 volts across those bulbs. That means my batteries, I've got two of them in there, have to add up to 135 volts. And so, if that's 45, this is gonna be 90 volts. Because 90 plus 45 is 135. Okay? Yes, sir.
So what would you hypothetically do if the inductor and the capacitor were working against one another?
I would still say the total current through the circuit is enough to make, bulb B 45 volts bright. The others are in series. I need a total of 135. And if that capacitor was somehow switched, it would be fighting. So the inductor would have to be 135 plus 45. So that when you subtract the 45, I'd get enough for the volts. Does that answer your question? There was a hand up in the back. No longer? Okay, again, that was your homework problem. That takes off a little bit of pressure as you're preparing for the exam. Remember, there are 2 sample exams at Max with the solutions. And so I would encourage you, as I always do, to take those seriously. Find a block of time when you can just devote yourself to one of those exams. And don't look at the solution key and don't talk to the people in the help center. Just take it as if it were real. And then grade yourself. Okay, then grade yourself. Okay. The next problem comes right out of one of those sample exams. And again, this is a problem with both an inductor and a capacitor. Only the difference is that here we actually have resistors with values, so we can get numbers for our current. And so let's do that. I really should have brought a copy of that problem. Okay, I'll just do it at the board. The first thing we're asked to find is the current through the battery right after we close the switch. So with your neighbor, do that really quick.
That means that our wire. That means R1. You're gonna go to R2. But we short out, we not go to R2. Now we have a wire. That's like yeah, R2. That is
Okay, did you get 9 amps? If you didn't get 9 amps, you need to look at your work again. Right after we close the switch, the inductor is going to act like an open switch, and the capacitor that's empty is going to act like a wire. And so this is my circuit. And so if I'm looking for the current through the battery, I know that all of the current has to go through R1. And then all of the current is going to go through the capacitor. Okay, so it all goes this way. And so this is part A. And so if I've got 180 volts across the battery, delta V equals IR globally. I've got 180 volts pushing current through, the only resistor in this loop is the 20 ohms. And so that's going to be the current through the battery is going to be 9 amps, and it's going to be up. Now, again, this is in your sample test problem. Whereas the magnitude and direction of the current through R2, R2 is shorted out, so that's going to be 0. If we want the voltage difference across the inductor, I can write the voltage across the inductor plus the voltage across the capacitor has to equal 180 volts. Any path from, if I take a path, it doesn't have to be a closed path, just any path from one side of the battery to the other, it has to add up to the battery voltage. And since the voltage across the capacitor is 0, that means the inductor has to have 180 volts across it. Okay. Well, now we leave the switch closed for a long time, and the inductor and the capacitor trade places. Now the inductor has stopped fighting, it acts like a wire. The capacitor is full, so it acts like an open switch. And so the circuit looks like this. So let's do part B. We've got so it's looking like that. So that means the current is going to go through the wire. R1 is shorted now, and then it's going to go through R2. And so that means my total resistance now is going to be 40 ohms instead of 20 ohms, what it was here. So that's going to cut the current through the battery in half. So I would have 4.5 amps going up through there. And then we want to know the charge stored in the capacitor. Well, the charge stored on the capacitor is just Q times the voltage across the capacitor. Again, we can take that same path that we chose last time from one side of the battery to the other through the inductor and the capacitor back to the battery. So again, the voltage across the inductor plus the voltage across the capacitor is 180 volts, but now it's the inductor that's acting like a wire. So that means the voltage across the capacitor is 180 volts. If I plug that into this formula, my capacitance is 0.75 farads times 180 volts, and that's going to be 135 coulombs. Okay, and the magnitude of the current through R1 is 0 because the inductor is acting like a wire and shorting it out. So now the switch has been closed a long time and we throw it open. And so in this case, what this thing looks like is I had this thing charged up, the capacitor, to 180 volts. And it has to stay that right after I throw the switch open. It takes time to empty that capacitor out. And so that's going to drive current around this loop. I know that I had 4.5 amps going down through this inductor in part B. Okay. And that can't change. And so that's gonna go around this way. And so the voltage of the inductor I can find from I've got to drive 4.5 amps through 45 ohms. And down here, the current is going to be 180 volts. This would be the current through R2. I can figure out what those are. Yes, sir.
Where did you get the 45 ohms from?
Good point. That came right out of my left ear, but that was a mistake. That's one mistake. If I make three, you get your tuition back. Okay. How we doing? Okay, that's enough of these inductor capacitor problems. Let's move on with our lives. If the magnetic field vector is directed north and a positive particle is moving east, what will be the direction of the magnetic force on the particle? So with your clicker again, let's
From the inductor going down.
if you look at the current here, if 4.5 has to come in there, 4.5 has to come up there, which means that there's not going to be any cross.
Going up, right? So now it's going forward. Yeah, I think it's more south. But there has to be that way. Yeah. I think it's very important. Yeah, the one. I know myself.
Okay, last call. So last call. Oh, okay. Good on you. Okay. So up is the correct answer. Evidently, we got that going for us. It helps to think in 3 dimensions, and some of us can just do that, without any props. But you know whether you're one of those people or not. If you are one of those people, maybe you should become an architect. Or someone that does things with, computers in 3D. But if you're not, bring props to, the type of props that they're gonna let you bring into the testing center. Extra pens or things like that. And then just, remember where you are. In this room, north is Canada. That we're at war with, okay? And that means that west, that's California. That we're also at war with, is that way, okay? And east, which is Boston, which we are also at war with, is that way, okay? So there's north, west, east, south, up and down, okay? So we're told that the magnetic field vector is going this way and that the particle is going that way. So I reach in the direction of the motion, I swing my hand in the direction of the B field, and my thumb is pointing towards the ceiling or up, okay? We have always been at war with Eurasia or East Asia. That's a quote from what? 1984. You need to read that book. Okay. An electron is moving in a horizontal plane in a region with an upward, by that we mean towards the ceiling, B field. Viewed from above, in what direction does the electron circulate? Clockwise or counterclockwise? With your clicker, please. This is not going to be on the exam, but if we do go to war with Canada, I know which side I'm going to be on. A, I'm going to be on Canada's side. Okay.
Because we're looking down on it. It's like imagine you're gone, down in your eyes.
Okay. Last call? Whoa. What do we do? I don't. Does the vice president cast the deciding vote? Or what goes on here? Oliver, do you get to cast the deciding vote? What, is that? Okay. That's worrisome. Let's 66 to 66. That just is amazing. That is the most beautiful result. If it weren't so troubling. Okay, so I'm the direction I'm the electron, and I'm going in the direction of my nose. Okay, and so I reach in the direction I'm going, and I turn my wrist so that I can wave in the direction of the B field, which is up, and that's going to be the direction of the force on me. If I'm a proton, if I were a proton, I would be going around clockwise as viewed from above. If you were looking down on me like a seagull looking for a target, I would be going clockwise. But I'm an electron, so I'd be going the other way. So the answer is counterclockwise. Counterclockwise.
We didn't have the right. Yeah.
Okay, there's a very high likelihood that you're sitting next to someone who voted wrong on that. Talk to them and convince them why they were wrong. Sure I can. I can draw that. So let's do it for a proton. If I'm looking for at a top view, the magnetic field is coming up towards us. So if I'm going like that, my force is like that. If I'm going like that, my force is like that. If I'm going like that, my force is like that. If I'm going like that, my force is like, you're seeing a pattern, right?